Welcome to this month's tip. This month we are going to continue our discussion from tip 70 entitled, You Don't Always Need a Hard Gauge. Tip 71. You don't always need a hard gauge to evaluate the surface method, Part 2. In tip 70, we showed the use of the surface method to evaluate a geometric tolerance that is applied at MMC or LMC. If you recall, we showed a simple built-up gauge or measurement with a CMM as two methods for verifying that the feature's surface does not violate a virtual condition boundary. For the surface method, this is the only requirement that must be met to evaluate the position tolerance. A hard gauge can be used for surface method evaluation, but we're going to continue talking about methods that don't require a hard gauge. This month we're expanding on this topic by showing additional ways to evaluate a geometric tolerance at MMC or LMC using the surface method. Our example has a position tolerance at MMC applied to two cylindrical holes. First, we will measure the size of the two holes and establish the datum reference frame, and we are going to do that with a coordinate measuring machine, or CMM. To evaluate the position tolerance for each hole, the CMM probe may then be moved to the true position for either of the two holes, as defined by the basic dimensions. Remember, the true position is not the name of a tolerance, so it is also not what the symbol in the feature control frame is called. That's a position tolerance symbol, which is right here in our drawing. True position is the theoretically exact location specified by basic dimensions. This terminology has been in place since the Y14.5 1973 standard, but incorrect terminology, sometimes calling a position tolerance true position, has lived on for quite some time. In this case, as we can see on the drawing here, the true position of both holes is 40 millimeters from the datum reference frame in the vertical direction. The hole on the left is 40 millimeters from the datum reference frame in the horizontal direction. The hole on the right is 160 millimeters from the datum reference frame in the horizontal direction. To use the surface method for evaluation of the position tolerance, the CMM can be used to measure the radial distance from the true position to the surface of the hole for as many locations within each hole as is needed. The number of radial distances that should be measured, which should be specified in your measurement plan, depends upon how imperfect the parts are and how tight the tolerances are. For each hole, we are looking for the shortest radial distance measurement to ensure that the surface does not violate the virtual condition boundary. Here is an image of a typical setup for this type of part on a CMM, with the datum feature simulators being the granite base of the CMM and a couple of angle blocks. We also see the CMM probe, positioned to measure radial distances within one of the holes. Remember, the virtual condition for these internal features, toleranced at MMC, is the MMC size of the hole minus the geometric tolerance. In this case, that will be 20 minus 0.1, which equals 19.9 millimeters for the MMC size, minus the position tolerance of 0.6, giving us a virtual condition of 19.3 millimeters. Each radial distance we measure must be greater than or equal to half the diameter of the virtual condition, which is 9.65 millimeters. Our result for this radial distance measurement method will be a pass or fail outcome. If the shortest measured distance is greater than or equal to 9.65 millimeters, then the result is a pass. If it is less than 9.65 millimeters, it is a fail. ASME Y14.45 2021, which is titled Measurement Data Reporting, provides a way to evaluate the surface method that also does not require a hard gauge. This method provides a variable reported value instead of the pass or fail result from the radial measurements method. The Y14.45 2021 surface method reported value for position at MMC for an internal feature is found with this formula. The reported value equals T, which is the specified position tolerance value, in our case 0.6, plus the difference between the virtual condition size, in this case 19.9 millimeters, and the location-constrained measured mating envelope, or LCMME size, which is based on measured data from each feature. Here is an illustration that shows a cross-section of an internal bore in a part. This provides a simplified view of the true position here in the center, some radial measurements to the surface of the feature here and here, the shortest of those measurements right here, the virtual condition, which is this cylindrical acceptance boundary that is blue in color here, and the location-constrained measured mating envelope, which is this other cylinder found from measurement data that is red in color right here. Do you see a relationship between the shortest radial distance and the LCMME? The size of the LCMME is just 2 times the shortest radial distance. With these methods, there is no need to make a dedicated hard gauge, and also no need to find the axis of the hole and determine if it meets the position tolerance. If the cost can be justified, and you prefer to use a hard gauge instead to evaluate your tolerances at MMC, then you would just need to make a gauge that has datum feature simulators, as shown in this CMM illustration, and gauge pins located at the true position for each hole, with each having a diameter equal to the virtual condition. For more information about how to tolerance those gauge elements, see ASME Y14.43, Principles for Gauges and Fixtures. Remember, at Tec-Ease, GD&T rules. See you next tip.